everyone, my name is Francis Arevalo. I am a 4th year CPE student at Bicol University Pulangi, and in this video we will try to discuss the output of laboratory activity number 1, plotting analog signals using NumPy and Matplotlib libraries of Python. Now this is the code for our laboratory number 1. Now the first thing we do is we import the NumPy and Matplotlib so that we can use it for our code. Here you can see it here. Next is now we try to create the time array. To create the time array, we use np.arrange. Here we have np.arrange. Now the conditions here are 0 to 1. This 0 to 1 is the range of our time array, and 0.001 is the steps or the data points in between the range. So we have 0 to 1 second and step of 0.001 second. After creating the time array, now let's define the sine wave. We define the sine wave using np.sin. Now for its condition, we have 2 times np.pi. np.pi is just pi times f1 times time. f1 is the frequency of the sine wave. Here we have a frequency of 5 Hz. Now after defining the sine wave, we now try to plot it using Matplotlib. So to plot sine wave, we use plt.plot. We use plt.plot. Here we have the time and the sine wave given, and its title, the label time as or the label on the x-axis, and the amplitude or the label at the y-axis. Here we can now see the sine wave of 5 Hz. We have the time array ranging from 0 to 1 second, and the amplitude and time. Now let's try to change the frequency of the sine wave to 10 Hz. As you can see, running the code, we can see that the sine wave with the frequency of 10 Hz has more number of waves, and the waves appear to be more compressed than the sine wave with 5 Hz. This happens because frequency controls how many times a number repeats, how many times a signal repeats per second. Now let's talk about the cosine wave. Same as what we did with sine wave. To define the cosine wave, we used cosine wave equals np, but instead of sine, we use cos for the cosine wave, and 2 times np.pi times the frequency for the cosine wave and the time. Now to plot the cosine wave, I used the same as the sine wave, but in the plt.plot, instead of sine wave, p and cosine wave, and the title cosine wave, the label time, and the y label amplitude. Now looking at the output, we can see the sine wave and the cosine wave are almost identical. That's because the cosine wave is just the sine wave but shifted 90 degrees. And as we can see in the waveforms in the output, the cosine wave is just the sine wave, but it has been shifted horizontally. Given the sine wave and cosine wave, when we try to add them, the result depends on their phase relationship. When both sine wave and cosine waves are in sync or their phase are the same, it reinforces each other, giving us a combined signal that is identical to sine wave and the cosine wave. But what happens when we try to change the frequency or the phase of either sine wave or cosine wave? Now, changing the frequency of sine waves to 5 Hz gives us a combined signal that is deformed. Now this happens because when they are out of sync, the cosine wave and sine wave tries to cancel each other out, giving us this deformed signal. Now let's go back to the time array. We remember that we have a range of 0 to 1 second and the step of 0.001 second. This 0.001 second is also known as intervals. Now what happens when we try to change the interval to 0.01? Now looking at the output, you can see that the waveforms appear more jagged. This happens because there are now lesser data points that we are capturing since we increased the intervals. And the lesser the data points, the more jaggedy the lines appear. This is called undersampling. Now what happens when we try to decrease the interval? Now we decrease the interval to 0.0001. Now looking at the output, we can now see that the waveform appears more smooth than the previous waveform. This happens because when we decrease the interval, we have now more data points, and the more data points we have, the smoother the signal appears. Now this is called oversampling. Now the amplitude affects how tall the wave appears. It controls the signal strength or the voltage level in real application. Meanwhile, frequency affects how fast it oscillates together. Together, amplitude and frequency define the basic shape and energy of our analog signals. To summarize, the output of our Python code changes based on frequency, phase, sampling rate, and amplitude. Using NumPy and Matplotlib made it easier to visualize and analyze these signals in the time domain. And that's how we understand why the output looks the way it does. And thank you for watching.